let's start again, and we'll introduce Jim Freitag. We'll talk about ranks and differential.
Right. So here's what I'm talking about. This is a quote from a paper of Tom and me. So Margaret Blake noted that empty set definable sets, so we'll have differential order 2. I'll explain more what this is. Laskar and Morley ranks are the same. And examples similar to the one produced above have order at least 5. Is there a theorem responsible for this gap? Might not make sense yet. But the goal of this talk is to explain that gap, which you shouldn't take out of context.
Looks like
and I'll try to
the gap between 2 and 5.
I'll try to explain either of these context, but I'll try to explain everything in very elementary terms by the end. So it's elementary is okay. So for model theorists, there will be some definitions which look a little unsophisticated, but okay. Just have to accept. Okay. All right. So first, let me set up the notation. So F and K will always be differential fields, always of characteristic 0, and U will always be a differentially closed field of characteristic 0, which is saturated enough. And the way it's described by Michael yesterday was it's very thick. So, and for me, a differential variety is just, it's an affine variety. Some people may say something like this. Affine differential variety, just the 0 set of some collection, finite collection of differential polynomials. And this is my notation for the differential polynomial ring over with coefficients in K in n variables. And this should be a script U. So it's a sub, I think about it as a subset of U to the n. And that's how I'll think of it. Okay. All right. And when I say constructible, I just mean a Boolean combination of varieties, those closed sets. And if I fix a Kolchin generic point, I think most people know what it means in this room, then I'm going to be working under the assumption that the transcendence degree of the differential field generated over K by that generic point is finite. Okay? So some people would call this being finite rank or finite dimensional or something like that. You can say the kinds of things that I'm going to say in more general circumstances, multiple derivations, where you don't assume anything about this, but I think that the definitions would be harder to set up. So I want to just work in this case for today, try to explain what I'm explaining. Okay. So the first thing I want to define is what model theorists call Morley rank, and I'm not defining it necessarily in the way model theorists would, but I'm trying to make the definition as elementary as possible given the background of the audience. So a set will have Morley rank bigger than or equal to 0 if it's not equal to the empty set. Okay, so always V here is a constructible set over some differential field. Differentially. And I'll say that you have Morley rank at least n plus 1 if you can find infinitely many constructible sets so that pairwise they're disjoint, and each of those is Morley rank at least n, and VI is contained in V. I left that out, but it wouldn't be much of a condition on V. So I'm making that assumption as well. Okay, so if you can find infinitely many disjoint subsets of dimension n, then U are dimension at least n plus 1.
Do they have the cover?
Pardon me?
Does the VI, do they have the cover V?
No.
Okay.
Just only what's written. So
okay.
Yeah. Okay. And you'll be Morley rank exactly n if the Morley rank of V should say greater than n. Sorry about that, but not greater than n plus 1. Okay? So try to give some examples and talk a little bit more about it. But we also sometimes call the Morley degree the maximum number of disjoint constructible subsets VI of V that have the same Morley rank as V. Okay, so it's say a model theoretic notion of degree. Unfortunately, it's not true that irreducible in the Kolchin topology implies Morley degree. But, all right. So, model theorists will often say V is strongly minimal if those two things happen. And in that case, you can see as a consequence of the definitions that every proper constructible subset of V is either finite or cofinite. Okay. So, because I'll leave it at that. You can see that just a little argument. Okay, so the point is that in general, calculating these quantities would be quite difficult. If someone hands you an arbitrary differential equation, it could be quite a task. But let's give an example. This was an example from earlier talk at the conference, so I guess all of the analysis was in Redialo's talk. But this was a system of nonlinear differential equations in 3 variables that she was considering. And okay, so here it is. It's a subset of u to the 3, or affine 3 space. And it was the case, we saw somehow, at some point during her talk, there were these 2 polynomials, h1 and h2, defined like this. By the way, the AIs are constants in this example, or just complex numbers if you like. And there's these 2 polynomials, h1 and h2, defined in the talk. And I think that she didn't say it exactly in the talk, but you can show that from the solution set, I call the solution set to this system of equations x, from the solution set x to affine 2 space of this script C means the constants for me, h1 and h2 define a map. Okay. And it's a dominant map. It's a non-constant. Okay. And if you just look at it a little, you can also see that this is an elliptic curve, and it's invariant under the vector field, which is what model theorists in the room probably call being a D subvariety. And because of that, well, you can, it's easy to prove that the Morley rank of this variety is 3.
So
well,
what do you mean invariant elliptic curve?
I mean that it's a D subvariety. You can cross out invariant.
Of
affine 3 systems. So from this, it's easy to prove that the Morley rank is 3. If you are looking for the families of subvarieties VI, you can think about taking the fibers of H1 or H2 and looking at intersections of those. Playing around. Not a hard argument. Okay. But everybody saw this system at least once already, so that's why I gave the example. Okay. Here's another rank. This one is harder to define, fortunately, because for model theorists it's really a rank on types, but we want to think about it for constructible sets. So I take U bar to be generic, and by that I mean Kolchin generic over K. Okay? So on this differential variety V, and I say that the U rank, or the Lascar rank, of U bar over K is bigger than n plus 1 if there's some differential field extension, F, containing K, so that the transcendence degree, when you move from K to F, drops. And it should be, if you're defining what bigger than n plus 1 is, it's an inductive definition that the U rank of U bar over F is bigger than n. So it depends on the field, and in this formulation on the field and the point U bar. Okay? And just like before, I made the same typo. There should be an n right here. So a point is U rank n, the Laskar rank n, if it's Laskar rank at least n by the first bullet point, and not at least Laskar rank n plus 1. Okay? So, sorry. This should say, are u over k greater than or equal to n? All right. We'll consider some examples so you can get a sense of it. Okay, then I set the U rank of the definable set, or the constructible set V, to be the maximum over all the points in V of the U rank. This isn't a good idea in a more general model theoretic setting, but it works fine here. And it's true in general that the U rank of V is bounded by the Morley rank of V. So a way to think about the U rank, if you want to think instead about subvarieties rather than extending the field, is that as soon as you have something like this happening, what it really means is that U bar satisfies some additional differential equations over F that it didn't define over K.
Actually, Jim,
Yes.
I mean, you start off with U bar generic, okay?
Yes.
Then later on you put RUV is max U bar in V. On the penultimate line. What do you mean?
Okay, okay, I'm sorry. Sorry. U bar can just be in V.
Anybody,
I'm
anybody.
sorry, thank you. Yeah, sorry. Sorry. U bar can just be an element of V. That's correct. Okay. I got ahead of myself. So, okay. If you want to think about subvarieties, anytime you have this happening, the locus of U bar over F is a subvariety defined over the field F of the variety V. And there's some uniformity there because it's only happening over this field extension. So all that matters is the actual isomorphism type of the coefficients that you use to define those additional equations. And because of that, you can build an infinite family of subvarieties. Okay, so you could try to set this notion up with just uniform families of subvarieties, but I think it'd be a little messier to say. Yeah, okay, and so this is related to Anand's question. Frank Benoit at some point asked whether the U bar which witnesses that maximum there could always be chosen to be Kolchin generic. The answer is unfortunately no. And again, I would say that this is generally a true statement. It should be quite difficult if you're given a nonlinear differential equation in general to calculate U rank.
What do you mean like no F? What's that no F?
No, by Freitag.
Oh,
That's my last name. I think this is standard.
by you, okay, so by you.
Standard sort of thing to write. Thank you. Okay, so there is an old example. Maybe one reason that Frank asked that is there's an old example of Poisson. So this variety, it only has one order 1 subvariety, x prime equals 0. And so you can see that the U rank of any transcendental element is going to be at least 1. But the U rank of both the generic points on x and the generic constants is 1. Okay? So if U is generic on x, it has U rank 1, and if U is a generic constant, it has U rank 1. Both of them have the same U rank. Okay? So just to go back again to this example from the previous talk, so you take this subset X in an affine 3 space. So if you think about the inverse image under the H maps of some constant, which is in a field extension of your original base field, so the C1 and the C2 are in some extension of K, then these witness the conditions that you need to show the generic type of that variety has U rank 3. Because what you're really doing here is restricting that generic type to some smaller subvariety each time. Because you can do this with any constants, you can do it with constants that weren't in K, And that's exactly what my definition required. Okay? So here's an example which shows. Here's the example I alluded to earlier. F 2012. There's a mysterious thing. It's if you pick a generic point on X, the U rank is 1. There's no way to extend the base field and lower the transcendence degree unless you lower it all the way to 0. But for a generic element in the subvariety X double prime equals 0, the U rank is 2. And that's easy to see as well, because if you're an element that says X double prime equals 0, then if you add to the field, so being generic on this variety, you satisfy some order 2 equation. If you look at U generic on this variety over K, and then you add to K the derivative of U, this is some constant, well, then suddenly you satisfy an order 1 equation over this additional constant. So, it's easy to see, it's easy to calculate things like U rank and Morley rank for linear differential equations. The only difficulty is for nonlinear things, at least in the ordinary case. Okay. All right. So why do you care? I mean, it might seem pretty, the definitions were a little weird, hard to calculate. I'm not doing a very good job selling why you want to do this so far, but here's some here's one of many reasons. Here's one example. So in a really nice series of papers, Ronnie and Anand showed that the second Pain-Levé equation, and they did many other things, is strongly minimal for anytime you take the parameter outside this exceptional set, 1/2 plus c. And here, just take the parameters to be coming as complex numbers, okay? For the purposes of this. I didn't state it. So later they used this to prove that there are no algebraic relations between solutions of P2 of alpha when alpha is generic. So when alpha is a transcendental. Okay? And Ronnie even strengthened that to include as long as alpha is outside of 1/2 plus c, but maybe is algebraic over Q. Okay, but not in 1/2 plus c. And the point is that as soon as you show more sets are strongly minimal, you can often get some sort of transcendence result like Ronnie and Anand's. So just recently I saw that P2 of negative 1/2, that's in the set 1/2 plus c. Okay, P2 of 1/2, it is not strongly minimal, but if you take away the exceptional subvariety here, it turns out that, I didn't write down the equation for P2, but we did have it in the previous talk again. If you take away the exceptional subvariety here, then the remaining constructible set is strongly minimal. So, and you can use that fact, pretty short order, to show that there are no algebraic relations between solutions of this equation. So you can do the same thing that Anand and Ronnie did, but on this exceptional set for the generic solution.
And the same is true for. And the same is true for all the exceptionals.
Okay, and
Sorry.
there.
Okay.
Okay.
Sorry, sir.
And you can extend,
Yeah.
of course.
Oh.
All right. So here's the question. Here's a question that was asked for definable sets in differentially closed fields. Do Laskar rank and Morley rank coincide? And then the earlier mysterious quote, Rashofsky and Scanlon, they gave a negative answer to this. The answer, I mean, their examples, it's a whole class of examples that are quite sophisticated, I'd say. And they use results of William, lots of other things. Yes?
And probably the answer is obviously no, but can you use the fact that this set P2, I mean, now you know that it has degree 2, so it's almost strongly minimal. Can you use then?
Pardon me?
It has degree 2. Can you conclude some results about the algebraic independence of the elements? No.
Yeah, well, yeah, sorry, I wrote that but maybe didn't say it. Yeah, you can show that for generic solutions to P2 of alpha, you can show the same result that Anand and Ryan. That's right. Okay. Yeah, so that's the point. Somehow, after you prove a strong minimality result, you expect to be able to prove something like that. Okay, so their examples had algebraic dimension at least 5, and so that means, I think I didn't define algebraic dimension yet, but for me, that is the transcendence degree of the differential field generated by a generic point on the variety. Or if you're working with an equation, a single equation in a single variable, it's the order of the equation. Okay, so roughly, there are order 5 differential equations for which Laskar rank is not equal to Morley rank. And like we said earlier, Dave and Anand had proved that for sets over the constants, Laskar rank equals Morley rank. And then it became a natural question to say what explains the gap, if there is one, between 2 and 5. Okay, so Dave and Anand used this result of Rashofsky, which I'll try to explain a little more in a minute, because it's hard to understand when stated this way. So if V is a differential variety over K, and K is a constant differential field, so I assume delta of A equals 0 for all A and K. Then there are infinitely many differential subvarieties of codimension 1, and codimension means co-algebraic dimension. So there are infinitely many differential subvarieties whose generic point has transcendence degree 1 less than the generic point of V, if and only if there's a non-constant differential rational map to the constants. Okay, so C of U, I mean the constants of U. Okay. So one direction is completely trivial to see. If you have such a map, then the fibers of that map give you an infinite family. Being non-constant enforces that it's actually a family, not just like one variety of something. Okay, so I've just restated the result, but maybe to state the result in a way that is more familiar to people not involved in model theory who never looked at Louis' manuscript. This is the statement of a special case. So if you take a vector field and 2 variables, P and Q have coefficients over complex numbers, say, then such a vector field has infinitely many Darboux polynomials, if and only if it has a rational first integral. So for model theorists, Darboux polynomial means D subvariety, basically, or it means a polynomial whose 0 set is a D subvariety, and rational first integral just means a non-constant map to the constants. Yes.
The dimension in the theorem is the algebraic dimension?
Yes. Yeah. And so here, the codimension 1 subsets are curves in the plane. Well, special curves in the plane. Curves in the plane where the vector field points into the tangent space. But this is a very classical theorem. I think probably well known to many people in the room. For instance, you can find a really nice proof of it in a paper of Michael Singer's. But I think the original result maybe was proved in the 1800s by Darboux. Okay, I'm guessing. Sorry.
So just trying to make sense of the theorem. So for example, does it say that there are no dimension 1 trivial sets defined over the functions?
I'm not, wait, sorry, can you say that
So
again?
if suppose that I have a dimension 1,
Yeah.
trivial in the sense of the
Yeah, okay.
set defined over the functions.
Yeah.
That would violate this theorem.
No, it doesn't. It doesn't. So this is an algebraic dimension 2.
No. So what I'm saying is that there's I mean the whole theorem.
No.
The statement of your theorem.
No, because there will be you'll have no K points on a trivial.
Okay, points. K points over K, thank you.
Yeah, delta subvarieties over K.
Okay.
So if you
Thank
want
you
to
very
count
much.
points, then it has to be K points.
Okay, got
Okay,
it.
yeah, so sorry for the confusion. Okay, yeah, it's extremely important that the field K here is a field of constants, or there's some restriction on it. It just can't possibly be true, say, for a differentially closed field. It's far from true. Okay. So there's this statement of the theorem, and myself and Raheem Musa proved, well, this is a special case of something we proved, but we basically, so I think this would have cleared it up for you anyway, but if instead of taking K to be a field of constants, you can take it to be a finitely generated differential field, even somewhere in the algebraic closure of such a field. Okay, so and you still get the same result, and yeah, and so.
You just said the subvariety is defined over K.
Oh, yeah, sorry. The subvarieties are defined over K. Okay. Here they're defined over K, and here they're still defined over K, even if I didn't write them.
Isn't any variety defined over such a thing? Any
Yes.
delta variety defined over
Yes,
such a thing?
it's true, but not all of its subvarieties are defined over such a thing. Okay? Yeah, so I'm not saying something about all the subvarieties over some field extension. I'm saying things only about the subvarieties.
So the U is over K as well? The U is
U is over
yeah.
K, sorry.
Ah, I see.
U defined
Okay.
over K. Like Alice and Tom pointed out, I think it just can't be true in general. Okay, so it's not that hard to see how from such a theorem, if you look at Dave and Anna's original argument, you just sort of use this axiomatically and do the same sort of thing. You can, and that lets you prove. So just to remind you, when I say their argument, I mean to prove that U rank equals Morley rank for sets of algebraic dimension 2. Okay, so now that's established, and so the question is, what about the other numbers in the gap that I'm supposed to explain to you about? Okay, so here's two possible strategies that I think are, maybe you could try either one. Sorry, not equal to. So two possible strategies for finding a variety with U rank not equal to Morley rank. You know lots of strategies for that. One of two kinds of behaviors would explain that. So the first one is that there's an infinite discrete, not somehow a uniform family of co-order or co-dimension 2 subvarieties. And maybe you'd want to enforce that there's no co-order 1 subsets just to be careful. In this case, you'd get something that has Morley rank 2 and Lascar rank 1. But I don't know an example of the second kind. I'm going to show you an example of the first kind that I came up with recently. So for an example of the first kind, I look at something that has many, many codimension 1 subvarieties, but the behavior of the subvarieties varies drastically as you range across the family. On many of so you take some parameterized family of subvarieties, and for most of the values of the parameter, you get Morley rank 1. But when C is in some sort of discrete set of parameters like Z or Q, you get Morley rank 2. And this is exactly one. Then in that case, then such a set would have Morley rank 3 and U rank 2. Okay, and so that's what we're going for. If someone wants to find an example of the second kind, that would be good too. Okay, so I'll tell you how I came to find such an example. So I'm going to consider a parameterized family of vector fields, just like before, and I'll let XC be the solution set. So here, P and C are either polynomials or rational functions in 2 variables over the complex numbers, and C is ranging over the complex numbers. Okay, so it's something simple. And what I want is, when C is in Q, I want the vector field to have infinitely many invariant curves, or D subvarieties, or Darboux polynomials, depending on what language you like. And when C is not in Q, I want the vector field to be strongly minimal or to have no Darboux polynomials or no D subdrives, depending on what language you like. Okay. Now, having this condition, it's almost equivalent, and I don't want to say what I mean by almost, but if you want to talk to me later, I can. It's almost equivalent to this model theoretic notion of a certain associated order 1 differential equation being non-orthogonal to the constants. And so that's really the condition that I'm going to think about, because it's easier to think about order 1 equations than order 2. So you can't use this theorem of Rosenleet, but we're going to do something like it. So Rosenleet considered differential equations of a very special form, order 1 equations, x prime equals f of x, where f is a rational function over a field of constants. And you can, this isn't how he stated it maybe, but that's non-orthogonal to the constants if and only if you can write this term 1 over f of x as a logarithmic derivative or a derivative. I'll elaborate on this a little bit more, but basically, non-orthogonal to the constants means that over some field extension, there will be a non-constant map from your variety to the constants. Okay. It's historically true that Kolchin and Shalab proved some specific examples which Rosenleet's theorem generalized right around the same time, and they were all trying to prove the non-minimality of differential closure. But the goal is now to understand when this is orthogonal to the constants. Something that's written in this form, in Rosenleet's theorem doesn't quite apply because, well, I mean, his only applies when you're working over a field of constants. And here there's something a little more general, but not much more general. D by dx of x is 1, so it's not a constant. So Rosenleet's theorem just won't apply to detect what I need to detect, but okay. I proved a sort of non-constant, parameterized version of Rosenleet's theorem earlier this year. So, so the condition looks very similar. Again, I'm characterizing this notion called non-orthogonality to the constants. The condition looks very similar, except there's this appearance of a delta 1 in the denominator where there wasn't any before. And delta 1, the notation just means it's the derivation obtained on k of x, where I extend the derivation on the base field, delta on k, by making x a constant. So you can think you're just differentiating the coefficients of the polynomial or rational functions in a way. It's a little more complicated, but not much. Okay, so why is this a little strange? So for the model theorists in the room, non-orthogonality to the constants, it wouldn't depend at all on the base field. But being able to be written in that form, it's kind of surprising.
What is delta 1? Oh, you say what delta 1
I
is.
say what delta 1 is.
Yeah.
But non-orthogonality to the constants wouldn't depend on the base field at all. But you would expect a condition like this, being able to be written in that form, might depend greatly on the base field, but it turns out that it doesn't. So one direction of this is extremely easy, and you do. So the direction of, if you are in that form, then being able to write yourself as being able to see that you're non-orthogonal to the constants. Let's just see that with the form on the left. So if you start to take the derivative d, so I extend, d is the derivative that extends the derivative delta on k and sends x to f of x. So if you calculate d of f of x, the partial derivative of v with respect to x, that's d of x plus v plus delta 1 of v of x. Okay, so by the product rule, you need to differentiate the coefficients, and you have to differentiate the variable. But now if you plug in what you know for d of x, this is dv dx. This is, 1 over f of x. This is now a minus delta 1 of v of x over dv Vx plus delta 1 of V of x, and the whole mess just becomes an A, which is just some element in the field. I didn't write that on the slide, but A is just an element of the field. And so if you took two solutions to your differential equation, and you look at the map V of x1 minus V of x2, it's a map to the constants, because they both have the same derivative. Okay. So, and the same, you can show the same thing, but for quotients of V of x1 over V of x2 in the second case. So the form in which you write it really is like a derivative or a logarithmic derivative in a way. Okay, and I mentioned this peculiar consequence. I mean, the non-triviality is really not to see that you can be written in this form over some field, but to see that already you can be written in that particular form over K. There's lots of ways in which you expect a set to be non-orthogonal to the constants. This says that that way comes about in a very specific manner. Okay. And so the idea for the counterexample is just to look, I used a computer algebra package, confess, to look for something where when a certain parameter is in some discrete set, you can write it in the earlier special form, and when a certain parameter is generally not in the discrete set, then you can't. And here's exactly an example. So there's an order 1 equation and the associated vector field that I take, and exactly the kind of behavior that I want happens. The Morley rank of this set is 2 if C is a rational number, and the Morley rank is 1 otherwise. Okay. And it's not hard to see from that the Morley rank of the total space, where you allow all C and the constants, is 3, and the U rank of the total space is 2.
So XC is a definable set.
XC is the definable set given by the vanishing of these two differential equations in two variables. XC is a subset of affine 2 space given by these two equations.
Defined over C of that.
C is a constant.
C varies over the constants.
C varies over the constants. And there's another way of seeing this, of course, after you discover such an example. So I discovered it by using this version of Rosenlich's theorem that I proved. But what's really the reason that it happens? Well, okay, if you say do something like look at solutions which are meromorphic functions by using Seidenberg's embedding theorem or something along those lines, then you can see that solutions of this equation obey that relation, where C1 is some arbitrary constant. And, well, if you exponentiate both sides of that equation, then it's exactly an algebraic equation when the C is rational. And that's exactly what you need to, as model theorists say, witness forking or witness the growth of the U rank. And I don't have any more time, but some of this is joint work with other people.
Could you put back the slide, just two slides where you state the main theorem? You know, 'cause it was,
yes. Yes. Okay. So thanks. That's it. And I'll go back.
Okay. No, RMC, if C is not in Q, or in Q, sorry, yeah.
In Q, rank 2.
Oh, are there other questions?
What about 2 and 4?
Oh, okay, so I tried to subtly signal that with this slide.
Don't worry about it.
But you shouldn't worry about it, because maybe you just take a product with an order 1 set. And,
Oh, okay.
or something.
Other questions?
Wasn't
ahead.
wasn't there a question of whether things come from groups or groups are involved? This is a counterexample to the issue of groups being involved, but there's no groups here. Right?
I'm sorry, I'm not sure I understand.
There's no
group involved.
I mean, there's no group involved here, right? There's no family of groups. It's very far from family.
It's very
These are
far.
trivial. These are trivial.
Well, I'm not claiming that, but yeah, I guess you could deduce that using similar reasoning to what you and Ronnie did with Penleve too, right? Because you could use the Rashofsky's-Kolovich type classification. I think so, but I didn't do that. I didn't write that down.
Well, there are no definable groups involved. It's your explanation on the next page makes it look like there may be something to do with analytic covering.
Yeah, I think that's safe to say. Yeah. There's something to do with it.
So does the answer knowing about n equals 5 imply anything about n greater than 5?
Yes, the nature of this question is if you answer it negatively for any value of n, then you will have answered it negatively for any higher value of n, which is why I have the vague advice.
In this case, the gap between the two ranks is 1, so one rank is one higher than the other. But you can have a higher gap between the two ranks.
I'm sure that you can. Yeah, I
guess
think.
it's
Yeah.
like sort of the
Taking
two
further
examples,
you
you
can
have something of rank.
Yeah.
Yeah.
Dimension 6 with a rank of, with a gap of 2.
Yeah, so it's,
But maybe he even wants to not increase the U rank while doing that, but you could kind of take a vibration over each of the special subrank. Yeah, okay. There's many things you can do, but increasing the ranks is usually the easier part.
Okay, well, thank you. And we'll start again at 3:50.